Welcome to the ChemDoctor, and this is the first video in the series on gases, and specifically this video is going to address Boyles Law and how to do Boyles Law calculations. Now, to set the stage, what I want to do here is I'm going to sketch a diagram of a syringe. All right, and most of us out there have we've been around syringes when we go to the doctor's office and we have to get an injection. And what I want you to think about here is that we're going to take this syringe that is closed and we're going to draw the plunger down so that we capture, as is stated in this problem. And my artwork is not going to be the greatest here. But later on I'll show you an actual video of this later on in this particular video. So here's my plunger. Alright, and what we've done is drawn it down to a point where we've captured 30 milliliters volume of air. So inside the syringe we've captured 30 milliliters of air by drawing it into the syringe. And in order to talk about Boyles Law, what I'm going to do next is seal the air inside the syringe. So over here on the right side of the screen, I want to remind the viewer of basically the four characteristics that we use to describe a gas. So here's a balloon. We can describe the pressure of the gas, which I'm going to define as P. All right, and remember that pressure is simply the force that the gas is exerting on the sidewalls of the container. So you can imagine blowing up a balloon, and when you blow up a balloon, you have to use your lung power to force the air into the balloon. So the balloon, the interior of the balloon, is under higher pressure than the air pressure that's outside the balloon. That's the only way that the balloon could actually have the shape that it does. The fact that it takes energy for you to transfer the air in your lungs into the balloon. All right, so the gas inside the balloon is exerting a pressure on the sidewalls of the latex. A gas can have a volume, and in this video and the other videos where I address gases, we're going to be assuming we're dealing with an ideal gas. And in an ideal gas, it's a very simple idea. We're going to assume all of the particles of the gas are widely separated, and we're going to assume that the particles are in constant motion. All right, and that's two of the factors that we assume in an ideal gas. Over the course of the video, we'll also talk about other issues as well. We can know the temperature of the gas. All right, and knowing the temperature of the gas is super important because because this gives us a handle on the kinetic energy of the gas. Just let me fix this error here. So basically, the kinetic energy of a gas, which we'll just abbreviate as KE here, is equal to 3/2 RT. Absolute temperature, so this is in Kelvin degrees. So it's important to know the temperature of a gas because basically what it does is it gives us a handle on the kinetic energy of the gas. And ideal gases only have one type of energy. They have kinetic energy. The fourth parameter that allows us to completely characterize a gas is to know the number of particles. And in this case, we're going to abbreviate that as little n. And in the case of gases, little n means moles. All right, so there are four main characteristics that allow us to basically describe a gas. Now, in the situation over here where I've drawn 30 milliliters of gas into a syringe and I've sealed the syringe, what we've done is we've established the fact that we know the total number of moles now, the total number of particles. That's what this represents essentially. So over the course of this example, the number of particles in the syringe is not going to be changing because we've sealed the syringe. The other thing that I want to briefly mention here has to do with the temperature. We're going to assume that the air that we drew from the room into the syringe is the same temperature as the temperature of of the gas that's in the room. So in other words, the temperature we're also going to assume is constant. So there's only two parameters of the gas that we've pulled into the syringe that are truly going to be what we call the variables. So in this initial gas, we know its volume, so I'm going to call it V1. And the other thing is we can extrapolate, or we can actually guess the pressure. Now I want the viewer to pause the video for a minute and think about how we can extrapolate or guess what the pressure is. All right, I assume you've come back and given this some thought. Since we drew the gas into the syringe and the gas came from the room, and we sealed the syringe without manipulating the plunger up or down, then the pressure of the gas that's trapped in the syringe has to have the same pressure as the room. So we're going to define our initial pressure here as P1, and I'm going to assert that it is the standard air pressure for an ideal gas, which is 1 atm. So we define standard air pressure being sea level pressure, and the standard pressure for a gas, I'll just put it down here in the corner. So standard pressure is going to be equal to 1 atm. And then make sure that you review your conversion factors, because 1 atmosphere is also equal to 760 millimeters of mercury, along with numerous other conversion factors. But in your course, the teachers probably already talked about these two pressure types, atmospheres and millimeters of mercury. So coming back to the syringe then, we've established that our initial pressure when we seal the syringe is the same pressure as the pressure of the gas in the room, and I'm assuming the pressure of the gas in the room, and therefore the gas that's trapped in the cylinder, is equal to standard air pressure, or 1 atm. And since I drew the plunger down to exactly 30 mils on the syringe, we know the gas's volume, because we assume the volume of the gas is simply the volume of the container. Now, to describe Boyles' law, and Boyles' law, if you haven't figured it out up to this point, relates the pressure of a gas to the volume of a gas. So what I'm going to do is just lay this idea out here right now. We're going to say that the pressure of a gas is indirectly proportional to 1 over its volume. Now, I know my writing is not the best, so the squiggly means in proportion. And you can see that I've said that the pressure of the gas is in proportion to 1 over the volume. What does this mean exactly? So here's what we're going to do. We're going to leave the syringe sealed, and I'm going to grab hold of my plunger with my hand, and I'm going to shove it up into the syringe, shifting the volume to V2. So let me go ahead and draw the picture of that. So here's my syringe again, and I'll try to replicate this as best as I can. Like I said, I'm not that much of an artist. Alright, so here's the syringe, here's my plunger. Alright, and I'll show it going to a smaller space in here now. Alright, and here's my the plunger handle. Alright, and I've shoved this thing up so that now my new volume, V2, is equal now to 20 mils. So we've decreased the volume by 20 milliliters. And the challenge that I want to lay before us is to find the new pressure, which is going to be P2. And before I get any further and confuse anybody, I've maintained the sealed cylinder. So my cylinder was sealed back here, and when we shoved the plunger up there to shift from 30 mils to 20 mils to make the volume smaller, the syringe has remained sealed. Alright, now with this said, what we're going to do is shift to another video, And in that video, I'm going to demonstrate in real time what we're doing here. And so very quickly, what I'm going to do is explain what you're about to see. So you're going to be looking at a syringe where you will that will have 30 mils of air that has been drawn into it. The syringe is sealed. You'll be able to see me compress the gas. In other words, shoving the plunger up so that we decrease the volume to 20 mils from 30 mils, and then you'll be able to see me let go of the plunger, and I want you to pay attention to what happens when I do that. All right, so with that, I'm going to go ahead and close this portion of the video, and we're going to shift. Okay, welcome back. And in the interlude there, we were looking at the demonstration of Boyles Law using a syringe. And now what we're going to do is go ahead and calculate the final pressure of the gas inside the syringe after we have shifted the plunger up from 30 mils to 20 mils. So we've decreased the volume, and I think I want to put some language on that. So we're decreasing the volume going from state 1 to state number 2. All right, and in the video you could actually see when I let go of that plunger, the plunger was forced back out, and the plunger moved backwards until the pressure inside the syringe equaled the pressure outside the syringe, and then the syringe stopped moving. So we can infer from what we saw, from the observation that we made, that P2 in fact has to be higher pressure than P1. So let me go ahead and establish that. I'll just write that up here in the corner. So P2 is going to be greater than P1. The pressure after we've shoved the cylinder in is going to be higher than the pressure that we started with when the cylinder was set at 30 milliliters. Now remember, at the outset of this, because we've sealed the cylinder, we haven't lost any of the particles of the gas. The number of particles has remained constant, and we're assuming that the temperature of the gas as we go through the compression, pushing the plunger in from 30 to 20, that the gas has remained constant temperature. All right, now, how do we find the formula for this? And just to remind you, remember that Boyles' law states that the pressure of the gas is going to be in proportion to 1 over the volume. All right, and my squiggly here means in proportion. All right, so what does that mean exactly? So coming back over here on the right, what that means is that if we have the volume of a gas and we decrease the volume, which is what we've done here, all right, we've gone from 20 mils to, or excuse me, from 30 mils to 20 mils. We decreased the volume. We could see in the video that the pressure had to have been increased because when I let go of the plunger, it shoved the plunger out. So that means that the pressure of the gas is rising in the opposite direction that the volume was going. So this little schematic right here illustrates how Boyles' law works. So the opposite scenario would be where we were increasing the volume, and in that case the pressure should actually be reduced, or it should be going down. So how do we calculate the final pressure of this? All right, for those of you that have been exposed to gases, you maybe know something about the ideal gas law, which is represented here, where all 4 variables of the gas is all in one equation. We have the pressure, we have the volume, we have the moles. So we have pressure, we have the volume, we have the molesies, and we have absolute temperature in Kelvin. And remember that the temperature has to be in Kelvin because Kelvin temperature gives us a direct line on the kinetic energy of the gas. And then you see we have this weird thing in here, the capital R. This is the gas constant. For our purposes, all you need to know about this is that this is the value along with some units that allows you to set all these variables into a singular equation. Now, why am I showing you this? Because we can actually derive the equation we need to solve this problem from the ideal gas equation. So let me just take you through that. For state number 1, we have the following relationship. We know that P1V1 is equal to nRT. All right, and for state number 2, we have a similar relationship, P2V2, which is also equal to nRT. Now, since we know that the moles and the temperature are the same for both state 1 and state 2, if I go through my equation, I'm going to put an asterisk above all of the things that are the same for both equations. Now, we know from algebra that relationship where A is equal to B is equal to C, then A is equal to C. This is probably one of those things you thought you're never going to use, but now we're going to use it actually. So let's go ahead and take a look at this. We're going to have P1V1, and it is equal to nRT with the red asterisk over the top, indicating these were the same for both P1 and P2. And this is equal to P2 times V2. So the Boyles Law the Boyles Law mathematical equation we need to solve this problem is going to be P1 V1 is equal to P2 V2. So now what I'm going to do is go ahead and solve the equation for my P2. So first I'm going to flip, because I always solve for my variables left to right. Then I'm going to divide both sides by V2. We see that my V2's on this side cancel out. So my final equation will be P2 is equal to P1 times V1 over V2. And now I can plug my numbers in. Now, your teacher or professor has probably talked to you about units, and when we go ahead and we plug into this equation, we need to make sure that our volume units are both identical, and we need to pay attention to the pressure unit that we've been asked to solve for. And I never said what it was we were solving for, so what we're going to do is we'll stipulate that we're solving for atmins or atmospheres, which we're already in that unit. So let's go ahead and plug the numbers in, and we're really careful when we do that to include the units. And my V1 was 30 mils. And we're dividing by V2, which is 20 mils. And we can see that P2 here is going to be 1.5 ATMs, 1.5 atmospheres. Indeed, P2 is greater than P1, which is the reason in the middle video that we paused for, you could see that plunger being pushed back out again when I let go of it because the pressure was higher. Now, before I go ahead and close the video, there's one other thing I want to point out here. If you look at the ratio of the two volumes here, all right, you can see the milliliters canceled out, so we solve for atmins, and then essentially we're multiplying the pressure times 3/2, which gives us 1.5 atmospheres. All right, so again, when we thought through this, we realized, okay, the pressure needs to be going up when we decrease the volume. So we can anticipate the fact that when we did this calculation, we should be arriving at a pressure which was higher than what we started with, and that's indeed what happened here. I would like to thank the viewer, for taking the time to watch my video. You can find more chemistry videos at www.chemdoctor.org. Thanks for coming, and we'll see you next time.